Welcome back to UVA Data Points. I'm your host, Monica Manning. Today we're bringing you a conversation within the third area of our model of data science, the area of systems. Systems is defined as the technological infrastructure that is required to carry out the practice of data science. Often associated with data engineering or machine learning engineering, the area of systems is concerned with both the hardware and software that supports data science. You'll get a more detailed description of systems at the start of the conversation, so we'll leave it there for now. In addition to the systems component, today's episode examines the recently published paper entitled From Biomedical Cloud Platforms to Microservices, Next Steps in Fair Data and Analysis. And to talk about this paper are two of its authors, Phil Bourne and Nathan Sheffield. Phil and Nathan both work within the domain of biomedicine, so a lot of their conversation focuses on that space. However, they take a fairly high-level view of the system's underlying data science initiatives, and so anyone who utilizes cloud services, remote computing, and APIs should gain knowledge from this discussion. And so with that, here's Phil Bourne and Nathan Sheffield.
Hello, everyone. My name's Phil Bourne. I'm the Dean of the School of Data Science here at the University of Virginia. I'm also a professor in biomedical engineering, which is actually part of the engineering and the School of Medicine. Prior to that, I was the first chief data officer at the National Institutes of Health. So it's a delight for me today to talk to Nathan Sheffield, who is now going to introduce himself.
Hi, I'm Nathan Sheffield. I'm an associate professor here at the University of Virginia. I'm a computational biologist. So my background from my undergraduate training and my PhD are both in computational biology. And I started here at UVA in 2016. And my group works on genomics. So I'm a faculty member in the Center for Public Health Genomics. And we work on a lot of data-related stuff, working to understand these new large-scale genomic data sets that are being produced now. And a big part of my group also works on more sort of infrastructure type work. So building the scientific computing things that we need in order to process this kind of large scale genomic data sets. And so that's kind of what I think led us to this interaction here is more that kind of infrastructure side of things.
Yeah, I mean, that's exactly right. And I'm honored to be part of the paper that it's really the nexus of what we're talking about today that is really your brainchild. A few of us just sort of tagged along, and we'll get to that in a minute. But let me just perhaps set a little context for that in the context with respect to data science and how we think about data science. This series, in fact, is built around our model of data science, which we call the 4+1, and it has different names, but that's one that sticks. And it's really the four major elements of data science, and the +1 are all the practical applications. We're going to focus a little today on practical applications that relate to bioscience, which is both of our backgrounds. But within the school, obviously, we're doing much broader than that. But the four areas, the obvious one is analytics, and that's what people often think about when we talk about data science. But there are three others which are really important. Value is one of them, which really talks about ethics and justice and policy and all the things that happen and bias in data and so on. And then another one is design, which is really around human-computer interactions, among other things. And then the one today that we're really focused on is systems, which is really the underlying components that allow us to do data science and perhaps the specializations we need within the hardware and software systems that we're using to actually make the most of data. So that's really what we're going to focus on today. So perhaps, Nathan, you could just begin with just giving a sense of what was the thought processes which led to the origination of this paper, which, as I said, I'm honored to be part of.
Yeah, the sort of ideas came out of just my experience dealing with, speaking of systems, dealing with the systems of how research computing is happening, now in biomedical, areas. And it's really a dynamic area right now. Things are changing really rapidly over the last 5 years, 10 years. mean, if you think about how research computing happened 15 years ago versus 10 years ago, 5 years ago today, it's not the same. Stuff's different. And so that's part of, I think, what motivated this is that as I'm trying to just get things done and trying to grapple with how do I find, where should I run my compute jobs? Where should I get the data that I need? And how can I make those things fit? As the amount of data has increased, it's leading to new challenges. So that's sort of the nexus of it. It's dealing with those challenges and trying to find ways to solve these things, which I think a lot of people are doing.
So, no one can see me, thank goodness, but I've been around this business for a long time, and I guess what I'm always struck by is the sort of the expansion and contraction in a way that relates to centralization versus distributed computing environments. And we've gone through various phases of that. I started when there was just a few big mainframes, and then with the advent of the mini computer, that changed things to some degree, and then the advent of workstations and PCs and changed it again. But at the same time, there was certain centralization of efforts, particularly as it related to data and other things. And then, it's kind of gone back and forward to some degree. Things like the Open Science Grid for computing really is a truly distributed environment. And then you have things like, which obviously, in a way that sort of is I wouldn't say the counter to what you're about to describe to us, but it is a piece of it. And that is cloud computing, which really is, in some senses, in principle at least, is neither centralized or distributed. It's just there. Maybe disagree with that. But that to me is sort of how I see the landscape that's evolved. I don't know if that resonates with you or not.
Yeah. I think that you sort of brought up, when I think about this, I think you kind of bringing up the technical side of things or the computing side of things and the way it evolves. And that's, I think, a big part of it is just, I guess, those models, right, for how we think about research computing, whether it's centralized or whether it's distributed or things like this. But I feel like that's one side of things, but the other side of things is just the amount of data, right? And so they kind of work together in the sense that if the data is small, like if there's not that much data, then it might make more sense to just spread it out or duplicate it, and then distributed computing is sort of makes sense. But if there's tons of data, then it becomes really hard to move, right? And then so you need to bring your computing power to the data, and this leads to a centralization. So I guess what I'm trying to say is that I think that there's these kind of centralization versus distribution on the compute side, just with compute power. But there's a similar dynamic going on in data as well. And so it's interesting to see how those integrate with one another.
Yeah, no, right? I agree with that completely. I think that the difference, of course, why we have data science is that there's just so much data, disparate data from so many different sources now. So it becomes a driver unto itself in ways that even bigger than it ever was before. Yeah. It's always, it's hard for us to put that into context because in genomics it's been around data. In a sense, to some degree, I'm putting up my hands here with with quotation marks around the notion of big data. But genomics has always kind of been thought of as big data, and it was sort of a driver in how we thought about this, and that actually led to centralization of data in the sense of around various resources that are supported nationally and internationally. So that's all interesting. And then the cloud came along. When I was at NIH, and this is a segue into your work basically, is that we pushed a lot on this idea of the commons, which you have interestingly to some degree pushed back on, and which is great because it turns out that three of the authors of the paper were all people who pushed the commons, but we were all happy to be part of the discussion that you're going to lead in a second. But just to the original concept. And I'll then ask you why you think it's not correct or it needs modification, was the idea of the commons was really this sort of simple idea that because of cloud services, you have this, this data would essentially be ubiquitous, and the idea, as would be the ability to compute on it. And so the idea was that it would all be done essentially in one place that was essentially unknown to you. And after you computed something in the commons, the output of that would potentially also be in the commons. And so it would become this kind of catch-all for the various kinds of computation and problems you were trying to solve. But what you point out in this paper, which we have to agree with, is not really how it worked out. So maybe that's a sort of lead you into what you think did happen and where you see what your work as described in this paper fits in.
Yeah. So when you use the word commons, in the paper we also use this word platform. And these words are kind of, I think, a little bit nebulous and not necessarily, maybe there's sometimes synonyms, sometimes there's subtle differences, but basically describing the idea of some kind of a compute environment where there's data resources and there's computing resources and there's specific tools, specific software. And so you can go there and do something, right? Do some compute on this data. So I guess they're commons or they're platforms, and maybe there's some subtle differences between those two concepts.
I would just say that, I don't personally, perhaps there are, but I'm not smart enough to see what they are. But, I think that the difference is that there's platforms and then there's sort of pipes. And the pipes are like silos of computation. The idea of platforms is that they're more ubiquitous than that. They're essentially cover more ground, whether it be in data or the ability to compute, than you would otherwise have. And I think what you point out is, in reality, that's not what's happened.
Yeah. Well, yeah. So getting on, I guess, to try to answer that question, I feel like the idea behind creating commons really is a good idea. It's that the data, there's so much data now that we can't possibly distribute it. So if we have it all in one place and then allow people to come, that solves a lot of problems. It solves the problem of distributing these huge data sets that are hard to distribute. It also solves problems of reproducibility because we can sort of control this environment. It makes it simpler. People don't have to run their own infrastructure. So I think all these are great motivations, and I think this is what has motivated a huge investment in these kinds of environments. But then now getting to, I think, where you're going with this, the issue is that there can't really be just one because there's too many different needs that people have, and people will always need to integrate across commons, right? And so that makes it actually more challenging in the end because you end up building these sort of individual, they almost become silos in and of themselves. And it's just, and what we argue in the papers is kind of an emergent property of a system where a lot of people are working on commons or working on these kinds of platforms because they start to become inward focused. They start to become focused on developing new features because they want to attract users. They want to increase the amount of data that they provide to increase their value. And so the focus is really on making that resource as valuable as possible. And the focus isn't really on making it connectable or interoperable with other similar resources. But if you end up with a lot of different groups building these kinds of resources, then what you end up with is the environment that I feel like we're kind of in or entering or maybe already in the midst of today, which is that there's lots of different common systems or biomedical platforms, and each one is kind of sponsored by and produced by a different group with a different kind of unique use case, right? And they're all kind of building those with the intent to try to solve problems for that group of users. And it's great if you can do everything you need to do in one of those. But if you find yourself needing to work with 2 or 3 or 4 or 10 of them, then you end up in this situation where you need to learn and understand all of these systems, and they're all slightly different. They might be built on different underlying cloud infrastructure, right? So they're on different clouds. One's on Google Cloud, one's on AWS, one's on Azure. And so you've got now different billing accounts for all of these that you need to manage. getting the data out of one and into a different one in order to do some kind of an integrative analysis becomes, maybe impossible, right? Because the data have to stay within one of the commons. And so this is, I think, what sort of led to this paper was just the realization that this is leading to some new challenges, right?
So I know you're itching to talk about the paper itself because we haven't even actually mentioned the keyword yet, right. But we will, and you will in a second. But I would just say before we get there that, as you know, we recently published a policy forum in Science, which actually, with some of the same authors of this paper, with the notion that to try and address in a different way some of the problems you've raised, which is really about having more consistency across these platforms, across agencies that fund them, and so on. The reality is that's given the response that the forum got, I'd say, which was virtually none. I'd say that it's kind of that's too big a leap. It's just not going to happen. Some elements of that may happen. But, to be honest, the various agencies who fund computing resources and the private sector are all going to agree on a set of particular ways of doing things? No. What you're proposing, I think, is an alternative, which is really interesting. So why don't you tell us about that?
Okay. So I'm not sure I would say it's an alternative. I guess it is an alternative. But in some sense, it's just a little bit orthogonal and could coexist. And we can get into that in more depth. I misspoke. I agree. And we'll get to that. We'll get to that.
So go ahead.
Yeah, but I guess the point here is that we want to talk about microservices and how microservices could potentially be, in some ways, I guess, an antidote to some of the challenges that we just talked about. So maybe we can just talk a little about what we mean by microservices. Right. So I like to just, when defining microservices, look back to the word itself, microservices, and try to figure out what it means just from that. And so what we're really talking about is there's two components, the micro component and the services component, right? And by micro, we just mean something very small. So in contrast to, a commons or a platform, a biomedical cloud platform, which might be trying to do lots of different things, right? Provide compute, provide big useful data sets, provide software, workflows that are actually installed, and you can come and run stuff, and you can analyze, and you can do everything there. A microservice is kind of on the other end of the spectrum in that it's trying not to do a lot of things. It's trying to do just one thing, one very simple thing, right? That's the micro part. And then the service part is bringing to mind the idea of something that's not running locally, something that's not sort of me doing it. It's something provided by someone else. So it sort of invokes this idea of something happening remotely, or it might not even be remotely. I mean, it might be like local on my computer, but it's a different instance that's handling that. So taken together, I think of a microservice as a small task that can be run, by something else and sort of used by me and called by me. And so there's some interface there that's allowing me to interact with it. So often this is happening over some kind of an API. So I might be able to execute some kind of a remote procedure or retrieve some data from some remote service, from some remote server somewhere. And it's just not going to do anything huge. It's going to just do something simple.
Yeah. Actually, the analogy you draw in the paper, which I like a lot because I've been around long enough to be, I wouldn't say at the beginning of the Unix revolution, but pretty close to it. And that, I just remember, there are elements in microservices in sort of the small and simple components that make up a Unix system beyond the kernel. And I think there's an analogy there. And I just remember actually being involved in writing books around Unix. There was a great book that was like Unix one-liners, which was actually this idea of piping together a whole series of very simple components to make a very powerful application, essentially, all in one line, one command line in a Unix system. So, I that's kind of the analogy that I draw in my head. I don't know if you, I think you see it that way.
Yeah, no, exactly. I think we even quoted in this paper from an early book about Unix, about how the power of a system comes more from the relationships among programs than from the programs themselves. Many Unix programs do quite trivial tasks in isolation, but combined with other programs become general and useful tools. And from my perspective, that Unix philosophy is part of the enduring legacy of Unix. Like, that's why it's still here, however many 5 decades later, operating in much the same way as it was. I mean, things have evolved, of course, but like the ecosystem is the same, right?
The philosophy is the same.
The philosophy is the same, and that is the philosophy of microservices. It's just it's kind of a rediscovery. I don't know if rediscovery is right, renewal of that philosophy, just in a different framework. Instead of on the command line, where the connection is the pipe, right? That can take the output of one of these, independently trivial tools, but when we pipe things together and we can build an ecosystem. The microservices, we're now doing this sort of with web. So the web, like HTTP, these kind of protocols are like the pipes, right? That are connecting microservices. And so you can build really powerful web applications through, by just piecing together microservices. This is sort of a systems way, getting back to this idea of systems, a systems way of thinking about an application and breaking it down into those individual components and then focusing on how they interact with one another. I think part of the value that you get from that is a reusability, right? Because if you just design an application that doesn't follow that philosophy, then the components of that application can't be then reused for other applications, right? But if you design an application out of small components that independently do something that is sort of well-defined, then that component can now be reused in another application. And so it makes building applications and interoperability across applications much simpler.
Yeah. You mentioned, we're talking about the application piece here, which is really the compute piece. But earlier, you also mentioned how data fits into this system, into the ecosystem. So, and you have some interesting ideas in the paper for how we think about data as well. So do you want to elaborate on that aspect of it?
Yeah, that's an interesting comment. I think maybe to pose that question in another way, how do microservices relate to data, right? Yeah. And so I think that you can kind of think of data similarly to what we were just describing. Sometimes we think of data as like this giant blob that lives somewhere, right? And we can go and maybe download that giant blob and then analyze it. And so maybe that's sort of like the monolithic approach to data. But an alternative way to look at it would be, could we index that data in some way make it possible to just, grab small pieces of it, right? So kind of like, I don't know, microdata, if that really makes sense, but that's sort of the idea, right?
So without losing the context of the larger data.
Yeah, well, and it depends on your use case, right? So for some use cases, you might need 100% of everything. And if you do, then, well, there's not much you can do about that. You got to have all the data. But actually, I think there's a lot of use cases for which we don't actually need all the data. What we want is either, specific pieces of data. So we call those data slices in this paper. So that might just be like specific rows in your table. And it might even be, a lot of rows, but it's not all the rows, right? And the more general and the bigger the data become, then the more likely it is that your use case only needs a subset, only needs certain rows in that matrix, say, for example. Or the other way that we can think about, I guess, retrieving the data in, smaller bits is through looking at summaries of the data. And so, like, for a lot of use cases, well, we don't necessarily need all the underlying raw data, right? What we really want is some kind of a processed version of it. So in the paper, we talk about this kind of funnel model of data where you have raw data that's very large, and then you might have some processed data that's still kind of large but not that large, and then you might have like summary level data that's very small. And so there's somewhere along that spectrum that the data becomes small, and for some tasks that might be enough. So the challenge becomes, how much data do I actually need? And how can we process the data and then make it available through microservices, right? Like through small function calls that just retrieve either subsets of the raw data or subsets of summarized versions of the data, right? And I think if we can do that, then we sort of view data almost the same way we view an application, where through access to whatever little chunks we need, we might be able to come up with increased interoperability, right, on the data side of things.
I mean, it's interesting, too, from the point of view of another aspect of how we think about systems within the School of Data Science is in aspects around security as it relates to data and the applications that run on that data. So in data slicing, in the way you're describing, it can actually also address some of the cybersecurity issues and the privacy issues by only allowing those rows that don't necessarily, for example, just making it very simple, that actually identify a patient, for example, in a system.
Yeah.
So yeah, I can certainly see merits in that.
Yeah, and this actually, the data security, I think, is a really interesting point, because this is another, I think, motivation for the sort of commons environments, is that if the data is controlled access, then having it in a centralized location, right, and making people come there to analyze it allows us to control it better. So that's sort of, I see that motivation for building platforms. And so somebody might argue, well, if you're allowing the data to leave, then you're no longer controlling it, right? And so there's some truth to that. But I guess the sort of counterpoint to that is that with microservices, through some of these modern authentication frameworks like OAuth 2, you can really nicely, authenticate and authorize people to certain pieces of data, right, like you say. And so you can allow data to move while still controlling access to it. So that's definitely possible and, is commonly done. So it's not the case, I think, that the microservices approach is not good for security. It's just that you have to think about it a little differently. And I think, like you said, actually, it might be the case that the raw data we have to control, but the slices or the summary level data we can make that available. And so if you just put it all on a cloud platform and say everybody using anything always has to come here, then you lose the ability for making publicly available some version of your data, right, that's going to encourage use of that data. Right? There's always some summary level that could be publicly available.
And that's absolutely critical to data scientists to have access to the data.
Right.
So yeah, it works. So are there? This is in some ways still quite formative. Would you say? Do you have applications already that you would point to that from your mind are either representative of microservices or close?
Yeah, sure. I think there's a lot. Here's like a simple example. We could create a service that, if you could look up information about a gene, say. So, let's say there's, a doctor or a genetic counselor that gets back a report from a patient who's come in and done some kind of genomic analysis, and there's some list of mutations and identify some gene, and the counselor or even a patient wants to learn more about that gene. So a microservice could just take as input a gene and could sort of look up some kind of data, information about that gene. So maybe at the more abstract level, it's sort of a doctor looking up information about this gene, right? It's a simple lookup system. Something like you'd type that into Google or whatever, but underlying those is actually some kind of a service running that people can then build tools on top of, right?
You reminded me of, I haven't been tracking it recently, but there was this notion of beacons where that came out of the GA4GH, the Global Alliance for
that's
Genome
right.
Health.
Yeah, I'm not super familiar with those.
But it was basically the idea that that people had all this human genetic variant information, and you couldn't access that information for privacy reasons, but you could make a service call to actually determine what a particular base call was at a certain point in the chromosome.
Yeah.
And you could do that across multiple resources. So you could build up a picture of the level of variation in that particular position across human population. And you could potentially get other forms of information, not patient information, but things like, racial, heretical type of information that relating to disease and things like that. So, I mean, I hadn't thought about it before, but that to me is, and that was quite successful. There was an instance where if there was a paper that came out which showed if you actually went to a single source and you actually queried that resource enough times, you could actually identify individuals within that resource. So that there's always one always has to. That's what we teach in data science. You always have to be on the lookout for these unethical and nefarious uses of data. Yeah. In the end, they stopped that by limiting the number of calls you could make to a given resource.
I see.
So, but anyway, that's getting into the weeds.
But actually, what you bring up is kind of, I think, where I was going to go with the gene example, because you sort of brought up the example of variance. But these examples are a little bit more like interpretation. But you could imagine similar kinds of things that a pipeline uses. So we run some analysis and we identify some genes that are of interest in this analysis, and we look up for those genes where their location is on the genome, say, right? So these are simple things that kind of thing you could easily just download gene annotations and look it up that way. But it's also something that it's the kind of thing that you could have a service that just handled that, right? And then all different kinds of tools that needed to say, look up locations of a gene, they can use this service. And these kinds of services actually already exist for basic things like this. So I think what we're proposing here is not new idea. Microservices are in use, they're active, they're right.
In a way, what you described, just to go back to the notion of a URL, I mean, it's basically a way to call a piece of information, but you don't know where that information is necessarily. You just have a unique way of calling it. Are there other aspects of this particular paper on microservices that we haven't covered that you think are important?
I think maybe one thing that we could talk a little bit about is the relationship between how microservices might fit into this ecosystem that we're talking about, where there's lots of, investment in commons environments and cloud platforms. So we talked a little bit about that because in a way, I think we've sort of set this, the way we've been talking about it, you sort of see microservices kind of the opposite of those in some sense. And I guess in some sense they are, but not really. It's not like these are two competing ideas. In another way, you could view microservices as the foundation of cloud platforms or of commons systems. There's lots of ways to build this kind of commons environment. And so maybe one of the questions is just how do we build it? Because you can, and people do, build a commons environment completely out of microservices. And if those microservices are also kind of made available externally, right, and are reusable and can be used for other things, then other platforms it will be much easier to integrate them, right?
You suddenly made me think of an app store, that you've got all of these simple well, they're not all simple, but applications that are available from one place, and you can go and choose one. And then you actually have to download it and run it. But if you were running it within that environment, that commons environment, that as opposed to taking it away and running it strikes me as the same kind of thing. You just have to have the ability to resolve and find the microservice that you want.
Yeah. The nice thing about that is that if people are sharing components like that, then whatever features are that rely on those components will kind of inherently work together then. And so in this sense, microservices aren't the opposite of platforms. I mean, in fact, they're just an alternative way to implement the goal of the platforms, right? But in a way that would encourage rather than make difficult, right, the communication across platforms.
Yeah. So I really set the stage badly for that in the beginning, but I've come around completely to the point of view that you just explained, and hopefully this is really useful to our students and others who are thinking about systems as it relates to what goes on in data science. So Nathan, what do you think would be the disadvantages of microservices?
The big, I think, maybe argument against using microservices is the potential lack of stability. Because the problem with us, I mean, the nice thing about a kind of monolithic thing where you control everything, right, is that you control everything, and so you can make sure it all works. Whereas if you start to, farm out pieces of that to an external microservice or whatever, right, to something, then now you're sort of reliant on that for success, right? So a system built out of microservices might crash if one of those services fails. See, so I think that there's a justifiable argument against building systems in this way that relies on, that basically says, well, you might lose some stability. And I mean, I sort of, go ahead.
Well, in the counter to that, again, I come back to the App Store notion that there's basically a standardization that goes on. I mean, to get into the store or to start with, you have to comply in a certain way.
Yeah.
So if you have a microservice, if you had some level of agreement across disciplines and so forth, that this was going to be some standardized features of microservices, the chances are that they're going to exist for a lot longer and be, continue to be reusable, is clearly going to be there.
Yeah. I think another way to think about that is like you kind of have to see who's providing the service. Like if it's got some like vetting, basically, then I mean I think essentially what you're saying is we just have to make sure that the links stay active. Like, right?
Yeah.
I think as long as that's sort of the point, I guess. As long as you do that, then I think you solve that major problem. But I think it is a reasonable challenge. So, if we're proposing a system where whoever wants to just goes out there and launch your tool as a microservice, and then if other people start to rely on that, then I mean you're well aware of the state of a lot of bioinformatics software.
Dead in the water.
Well, yeah, it's just like the way it's developed, and people move on. And
you made me think about you can never get away with these things without talking about incentives, and the incentive for putting something in the App Store is quite often financial, but the incentive for creating a microservice, say in genomics or in more generally in biomedicine, ultimately you can measure the usage of that microservice, and if that was credited appropriately, and that's to say we're not really doing a good enough job with software in accreditation right now, or in crediting the authors. But that's starting to change, and then this is kind of a whole new world order. It's sort of like a micro credit potentially.
Yeah. But that's I mean, you bring up a really good point, and I think that's part of what's driven investment in more self-contained systems, is that it's a lot easier to kind of sell something that's big and does lots of things, and now a lot of people want to use it, and now I can get funding for it. Whereas if you're working on like just something that does just this very small thing, people might, you don't get the credit. You don't get the reviewers aren't interested in that. Nobody's heard of it. So there's a social aspect here. Yeah. So you bring up, I think, a good point, which is how would you incentivize microservices? So that's another challenge, I think.
Yeah. Well, I think it's all tied into how we think about the scholarly output, or whatever output it is in academia. It's really scholarly output. That's no longer just papers. It's clearly good data sets. It's software. It's protocols. It's workflows. It's a whole variety of things that I would say that in the School of Data Science we are pretty adamant on recognizing those as important scholarly products, up there with papers and other things. So that, but it's a cultural shift.
Yeah, and it's harder to count those things,
yeah,
right?
Yeah.
So.
Yes, the metrics for it and the evaluation of it are still very problematic. Oh, this has been fascinating. So congratulations again on the paper. It's clearly,
Thank you.
I think we've come around to the notion that microservices and platforms and commonses and clouds. That's all part of a system-wide ecosystem. The winners and losers are yet to be established. But clearly, as you pointed out right in the beginning, the environments are changing. They're changing rapidly. And I think data scientists really need to keep up with those changes and be prepared to take the maximum advantage. So Nathan Sheffield, thank you very much for speaking with us today.
Yeah, thank you. Thanks for the invitation. Great. Thanks for the your contributions to the paper, and also thanks for the invitation to chat about it for a few minutes here.
All right. Thank you. Bye-bye.
Thanks for checking out this week's episode. We have a link to the paper Nathan and Phil discussed in the show notes. We'll be back on December 1st with a conversation in the area of analytics, but keep an eye out for a bonus episode in the meantime. If you'd like to learn more about the UVA School of Data Science, visit us at datascience.virginia.edu. And if you'd like to contact us, send us an email at uvadatapoints@virginia.edu. We'll see you next time.